Um, Hi everyone, my name is Khan, and today I'm going to be presenting the final project I did in the numerical computation class with Dr. O. And what I did is solving time-dependent Schrödinger equation using some of the techniques that we learned in class, specifically for the finite different methods and the Runge-Kutta method. So to start with, this project, it's going to be the numerical simulation rather than the data analysis. But because it's a simulation, I'm also going to do a little bit of the area analysis as well, and I will talk a little bit more later in this presentation. So let's get started with the background. So the equation that you see here is called the time-dependent Schrödinger equation, and it's really important in physics because it gives us information about the particle, specifically the momentum and the energy of the particles. And as you can see here, we have the first partial derivative with respect to time. We also have this Laplacian operator, which is the second order partial derivative with respect to the spatial components. The VI here is the potential function, and the psi RT here is the wave function. So by solving this time-dependent Schrödinger equation, we will get the solution of this wave function respect to the spatial part as well as the time part. So technically it's telling us how the wave function evolves over time. And for the people outside of physics, you might be wondering why I use the word wave function. So like technically in the classical world, like around us in the microscopic scale, we can see exactly where the particle is. I can see you by my eyes, but if you go down into the quantum level in the microscopic model, particle can behave like a wave, and because of that, we can't say exactly where the particle would be. But however, we can get the information of the particle by solving for this wave function that's going to give us the probability of like finding particle in one place over the other. And this wave function depends on the potential that it's bounded to denote by the V here. And therefore, this project is going to be investigating the numerical approach using the finite different methods as well as Runge-Kutta. And the reasons that we want to do it numerically is because solving this equation algebraically can be really difficult depending on the potential function here. Let's go to the next slide. So this is some of the backgrounds of the finite different methods and the Runge-Kutta method. So on the top here, we have the description of the central difference, which is the idea of expanding, uh, the idea of evaluating the function at one point by expanding it out using a Taylor expansion. And here we have two lines. We have the function evaluated as the next spatial point step, as well as the function evaluated at the previous spatial step. And by expanding it out, we can see that we can extract the second derivative on the third term here by combining these two functions together, which is going to give us this whole central difference formula. And the reasons that we want to get this approximation here is that if we look into the time-dependent Schrödinger equation, the Laplacian operator here is going to be technically second order partial derivative with respect to the spatial part. And by having this approximation, we can plug that into the Laplacian operator to evaluate our wave function at some specific spatial point. Um, Another thing is that once we get the approximation on the Laplacian operator here, we're gonna evaluate the whole right-hand side of this time-dependent Schrödinger equation with respect to the partial derivative to time here by doing the Runge-Kutta method. So the capital F here is going to represent everything on the right-hand side of the time-dependent Schrödinger equation. The small f here is going to be our wave function right over here, and t with the superscript tau means that we have the wave function and the right-hand side of the time-dependent Schrödinger equation at the initial point. Let's say we can have tau equal to 0, and by running the Runge-Kutta method, we can get the wave function at tau plus 1, which is the next time point in our evaluation. So as I said before, this project is going to be simulation-based, depending on the potential, and there are 4 cases in general that I'm going to be talking about. The first one is going to be the one-dimensional infinite square well. And this is the most simplest form to solve because we just assume that the potential is going to be zero inside the well. And you can imagine the box or the well being something like this shape. So at the bottom part, the V is going to be zero, but at the wall, V is going to goes up to the infinity, which means that the wave function is going to be bounded by this well. And as you can see on the time-dependent Schrödinger equation here, we don't have any potential dependence on the wave functions, and we can solve it algebraically, which I'm going to be talking in the next slide. The second case is going to be still in one-dimensional, but we consider the harmonic oscillator, which is a little bit more complicated because like here we have the potential that depends on the spatial part, which is x squared here. Once we plug that into the Schrödinger equation, we get this a little bit different form here. The first part here comes from the Laplacian operator that I said before, and the second part here comes from the potential. And we can also solve this wave function solution algebraically as well. And I'm going to be talking about it in the next two slides, maybe. We can also do the same potential for the infinite square well and harmonic oscillator, but in two-dimensional. And the only thing that's going to be different from the previous two cases is that when we look at the Laplacian operator, instead of having only one second partial derivative with respect to x, we also have the second partial derivative with respect to y as well. Similarly, on the fourth case, when we have two-dimensional harmonic oscillator, here we have potential that depends on both x squared and y squared, and the Laplacian here is going to also be replaced by x spatial x component and y component as well. So let's look into the first case of one-dimensional infinite square well. The left side here, I have all the exact solution that we can solve out algebraically. The top line here represent the spatial part of the wave function, because as I said before, the wave function is going to be depending on both time and space, and this is going to be responding to space. We also have the energy of the wave function represented here, and in order to get the full exact solution, we can combine the spatial part and the time part by doing e to the negative IENT over h bar here. H bar here is some physics constant that we don't have to worry about it. But essentially, as you can see here, we see that the exact solution is going to be in the complex term, which means that in quantum scale, all the information about the particle is going to be encoded in both the real part as well as the imaginary part. And in order to compare to the exact solution, I'm going to be looking into the real part of this exact solution, which can give us this formula. The first part here, we see that we have psi that has dependency on the x component. We also have the cosine that has dependency on the time part, which means that if we capture one specific time, we're going to see the wave oscillating in the x-axis, which is what we see here. We see the sinusoidal wave function as we vary the value of x. On the plot here, I also have 5 lines in total. Each has a different colors, and that represent the wave function at different times. So we start at the blue line here, and the next time is when the wave function become the orange line. And as you can see here, the wave is kind of switching or oscillating over time as well. And this match up with what would we expected, because we see that the real part of the wave function has the sinusoidal dependency on both x and t. So you can think about it in terms of like the cosine term is going to change the amplitude of the wave, and the sine term is going to give us that sinusoidal oscillation. We can also investigate further into how would our approximated wave function be different from the exact solution. And I do some analysis on all the plots that shown on this slide. On the top part, we have 3 plots here. The left one is going to represent the real part. The middle one is going to be the imaginary part. And the third one here is going to be the probability density of the wave function, which is technically the norm of combining the real part and the imaginary part together. And let's look into the real part first. The dash orange line here is going to be our exact solutions algebraically that we solved, and the blue line here is going to be our approximated solution. And as you can see here, there are a difference between these two lines, which is what we expected, because we can't really expect numerical approach to be exactly the same as the exact solutions. And if we look into the imaginary part, we see it's probably hard to see, but we see a tiny difference between approximated solution and the real part. However, if we look into the probability density, we see that it's almost matched up pretty well between the exact solution and approximation, which is good because in physics, we want probability density to be constant no matter what time we evolved. Things get really interesting when we look at the bottom two plot here. Let's take a look on the left one first. We have three lines here. The dashed green line is going to be the normalizations of the probability, which is supposed to be one in the physical sense, because if you sum up all the probability that you can find a particle throughout the whole region, it should sum up to one. So the probability couldn't really go above one or go below one. If it goes below one, it will mean that we lose some information about the particle, which is not really physical. However, if we compare the dashed green line here with the orange line or the blue line on the bottom, we can see that the normalization of the probability that of our approximated solution is a little bit lower than one. And this makes sense because when we do this approximation, we discretize the spatial step into the smaller subset. So we can't like exactly match up the curvature of the oscillating wave. So we always going to be under evaluating the area under the curve of the wave function, which give us a tiny bit smaller in terms of the normalization probability. The most interesting thing is on the bottom right plot here. Here I show you the area between the approximated and the exact solution in the real part showing in the orange and the imaginary part showing in blue here. And as you can see, the area doesn't just keeps going up, but it's actually oscillating between the real part and the imaginary part. So like once we see the maximum area in the real part, we can see the lowest area in the imaginary part, which is very interesting because I think it's because when we doing this approximation of the wave function, as I said before, it's a complex form. So when we approximate them at the same time, we kind of like have these two form combined together, the real part and imaginary part. So like once you over evaluate it on the real part, it's likely that you're gonna be less like under evaluated on the imaginary part. So like the error is kind of shifting between the imaginary part and the real part, which is I think really interesting. So like if we connected the bottom right plot here back to the first 2 point here, we can expect that it's not always the case that the real part will have the higher error compared to the imaginary part, but it's actually going to be depending on the time that we evaluating it. So like let's say if I change the time step on these two plots, it's possible that I'm going to see higher deviation in the imaginary part compared to the real part as well. So the second case is going to be one-dimensional harmonic oscillator. And sorry, excuse me. As you can see here, for the harmonic oscillator, the exact solution gets a little bit more complicated because like now here on the spatial part, we have this harmonic polynomial, which is some dependency on the polynomial function evaluated by this tiny hn eta here. And we also have the energy of the wave function. And we can also do the same trick. If we know the energy of the wave function and we know the spatial part, we can calculate the full solutions of the wave function that can be expressed in this form. And as you can see, it gets a little bit more complicated. However, the underlying nature is gonna still be the same. The first, if we look into the real part of the wave function, the front term here is gonna be responding for the spatial part that's gonna be encoded in this Hermite polynomial. We also have cosine dependency on time here, which is going to be responding for the wave like oscillating over time. And as you can see on the plot, here we have different lights for different times. And as you can see, at t equal to 0, we have the blue light here, which is you can't really see it behind the brown light here. So we have like 3 peaks or 4 peaks in total, and as time evolves, this space kind of like shifting back and forth in time. And not the only, but the main difference between the harmonic oscillator and the infinite square wave is that in the infinite square wave, we have exactly boundaries in which we want the wave function to dissolve, let's say from 0 to L. However, for the harmonic oscillator case, the wave function actually extended to the infinity and is supposed to die off at the infinity. However, during this numerical approximation, it's really difficult to set the wave function to be 0 at the infinity. So what I did is that I set up the range around -5 to 5 or -7 to 7, such that I set those conditions of the wave function to be 0. Because as you can see on the plot here, the wave function almost dies off to 0 already around -5 or 5. So it doesn't really affect the approximation of the wave function. So we can do the same trick of comparing the real part, imaginary part, and probability density of our approximation to the exact solution. As you can see here, again, the dashed orange light is going to be the exact solution, and the solid blue light is going to be our approximated solution. As you can see here, we see a tiny difference in the real part, barely any different in the imaginary part, and almost match up probability density of the exact solution and the real part. And the normalized probability of our approximation is still going to be a little bit lower than the exact solution, which is not exact solution, but to a physical interpretation of having normalized probability to be 1, which is what we expected if we solve, if we integrated using like the infinite point to integrate. But since we discretize the space, again, we don't have that accuracy. And if we look into the error comparison between the imaginary part and the real part, we can still see that oscillating behavior of error shifting between the real part and the imaginary part. Another thing that difference from the infinite square wave is that the green line here represent the magnitude of the wave function, which is when we calculate the norm of the wave function, this doesn't really stay at 0 anymore. And I'm not quite sure why. I think it probably has to do with some like physics interpretation behind it, but I don't have time to really investigate it. But that's something that I really want to look into the future for sure. The third case, again, is the infinite square wave, but now we have 2 dimensions. So the wave function in a 2-dimensional case doesn't actually, it's not really that complicated as we would think. Technically, we can multiply the spatial part of the wave function together for each dimension. That's why we have 2 side terms here. We can combine the energy together by just adding them together, and we can get the exact solution as shown on the bottom part here. Again, we have 2 psi function that's going to be representing the oscillation in the x-axis for the first term, in the y-axis for the second term. And the cosine term here is going to represent how the wave kind of like oscillating in time. As you can see here, we start at t equal to 0, and then the amplitude of the wave tends to like, not tend to like, but it's decreased over time, and then it goes to the opposite direction. It's go back to the neutral positions and then just like oscillating up and down as time evolves, which is what we expected by the behavior of the wave functions. And once we look into how the exact solutions, which is shown on the right plot here, the right column is going to be the exact solutions, and the left column is going to be our approximate solution. And as you can see, we barely see any difference between the real part of the wave function, but if we look into the imaginary part, we see a tiny difference. So our approximation is going to be a little bit like higher compared to the exact solution, but the probability density between those two is almost identical. And if we look into the error difference between the exact solution and approximated solution, again we see the oscillation in error between the real part and the imaginary part, which is match up with what we see before in the 1D case. And lastly, the 2D case harmonic oscillator. This is really looks really nasty for the final wave function. As you can see here, we have two Hermite polynomial that's going to be responding for the spatial part of the wave function, and this cosine term here is going to be representing for the oscillation in wave. And once we start at t equal to 0, we see some sort of like a symmetric in the x and y axis. But as we evolved over time, the errors comes in, and we see that the wave function tends to like disperse it, and it's not really well approximated anymore. So let's take a look into the area. Again, on the right side of this presentation, I have a plot comparison between the approximated solution and the real part. And specifically, if we look into the imaginary part, we see lots of area between the exact solutions and our approximated solution. And if you look into the plot right over here, we see the oscillating behavior again for the error shifting between the real part and the imaginary part. The error of the magnitude also increase over time, which is might be the reasons why we see a lot of difference between these two plots. So in comparison, we can technically say that our numerical approach able to simulate the oscillation of the wave, which is what we expected. And the error due to this numerical approach technically increase over time, but we also see this weirdly but interesting error trend line between the real part and the imaginary part, which is really interesting. And I'm probably going to plan to investigate this area a little bit more. So that's it. This is my reference that I use for this project. Thank you.